At this point, we have three ways of dealing with the data that comes from our experiments. If regression analysis shows that we have a line, that a line is a good model, then we just go with the equation of that line as our mathematical model. We have also seen that sometimes we have an upward curving graph we call a parabola. That's a square dependent relationship, and we found that if we square the independent variable and then replot, the slope of that line is a constant that relates the dependent variable to the square of the independent variable. Then we also found an inverse proportionality or inversely dependent relationship. In a case like that, we have a downward looking swoop, it's called a hyperbola, and we found that if we take the inverse or the reciprocal of the independent variable and plot that against the dependent variable on the vertical axis, if that straightens out and makes us a line, we can take the slope of that line, and that's a constant that relates the dependent variable to the reciprocal or the inverse of the independent variable. The type of nonlinear model that we're going to explore today is called a square root dependent relationship. You probably can figure out already what that might mean. Hopefully by the time we're done, everyone will understand why it's called a square root dependent relationship. So again, the question that we're asking ourselves is, what if a line isn't a good model for our relationship? We always have to warn ourselves that sometimes it's just not possible to get a good model if the data is so random that we can conclude that it's not related. The independent variable does not affect the dependent variable. And in those cases, we just have to give up on getting a good model. But that's not always the case. In fact, in well-designed experiments, that's often not the case. Let's take a look at an example where it isn't. This is an example of a balloon leaking, and the density is given in grams per liter, so these are different gases that have different densities, and the time it takes for the gas to leak out of the balloon is measured in days. It looks like the heavier the gas is, the longer it takes to leak out of the balloon. Let's plot this data and see what we get. With a straight line on here, a best fit line imposed on this graph, it doesn't look like a line would be a good model here. Doing regression analysis agrees with that. The R squared and R values are not really good. But it's not because of randomness that this isn't a straight line. Instead, there's a definite pattern here. If we sort of trace through the points, can't see them all because my box is on top of it and I can't draw down here for some reason, but there's definitely like a sideward opening swoop going on here. As always, we want to look for a math pattern that will help us linearize this data. Here's some numbers, some x and y values. Do you see the pattern? You may notice that each of the y values is the square root of the x value. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3, and so on. When we plot this, we get that shape that's like the shape we got from our balloon leaking data, sideward opening curve. So, because each of these values of y is the square root of the x values, if we replot this and put the square root of x instead of x on the horizontal axis and put y up here, we will in fact get a line with a slope of 1 because every square root x is exactly its corresponding y. Look for a math pattern here. What do you see? This is a little more subtle than the last one, but it's related to square root again. If I take the square root of 0 and then I multiply it by 3, I get 0. The square root of 1 is 1 times 3 is 3. The square root of 4 is 2 times 3 is 6, and so on. When I plot this data, this is what it looks like. There's that same characteristic sideward opening swoop. And if we were to take all of these x values, take their square roots and plot that as the horizontal axis variable against y, we would again get a straight line. Now the slope of this line would be 3, it wouldn't be 1 like it was in the last example, but it would still linearize the data. And it turns out that no matter what we multiply or divide the square root by, any constant, or if we add or subtract to it, we will still be able to linearize the data if this is the kind of a relationship that we have here, a square root dependent relationship. Let's go back to our example and see if it actually works for our data, because it did look like that shape. So in the pink row here, I've taken the square roots of all the densities, The unit ends up being square root grams over liters, which is a little bit funky, but that's what it is. Let's take a plot, and sure enough, it gives us a straight line. Regression analysis shows us that we have a nice straight line here when we plot the square root of the independent variable on the horizontal axis and the dependent variable on the vertical axis. Now the slope of this is what relates the leak time to the square root of the density. And so there's our mathematical model. We can find the leak time by just taking the square root of the density of any gas, multiplying it by the slope of this line. That's where this number comes from. It's just the slope that's given for the best fit line. And this will predict the time. Units are a little bit crazy here. The square root of density would be square root of grams per liter because that's what density was measured in. So that's all going to cancel out. And it just leaves you with days, and that's what time is measured in. So it works out in the end, even though the units look a little bit crazy. So let's summarize. If you have a scatter plot that looks like this, you might try to take the square root of the independent axis variable and replot. If that gives you a straight line, the slope of that line is a constant that relates the dependent variable to the square root of the independent variable. I should throw a warning in here. If you do more sophisticated data analysis in a future class in your future life, you will find that there are other mathematical models that have a shape that looks kind of like this one. So you'll have to be forewarned of that. But in this class, you won't find this shape of a scatter plot being anything other than a square root dependent relationship. So now we have a fairly complete set of tools, good enough to get started in our class now, analyzing real experimental data. We have 4 things we can do with experimental data. If it's a straight line, just use the equation of that line. If it looks like it's an upward opening parabola, an upward swoop, that's probably square dependent. So take the square of the independent variable, plot that against the dependent variable, and use the slope of that line, if it's a straight line, as a constant that links the dependent to the square of the independent. If you have a downward swoop, a hyperbola, that could be inverse dependent. So take the inverse or reciprocal of the independent variable and plot that against the dependent variable. If it straightens it out, then take the slope of that line, and that will relate your dependent to the inverse or reciprocal of your independent. And now in this video, we learned that if you have a side opening parabola, a side opening swoop, you can take the square root of the independent variable and plot that with the dependent variable on the vertical axis. And if you get a straight line, the slope of that line is a constant that relates the dependent variable to the square root of the independent variable. Now there are more sophisticated mathematical models that can be built. And in fact, you may find that you have to do more than one of these transformations. Like there may be a case where you take the square root because it looks like a side opening parabola, and then you find out that it looks like an inverse. And so you take the inverse of the square root, and that gives you a kind of a more complicated model. We won't run into things that are that sophisticated in this class, but basically the techniques that you learn are a good starting point for how scientists analyze all the data that they take to develop predictive models.